Hi guys, you're welcome to God Academy. In this session of our bootcamp, I'll be taking you through the second part of function. In our previous lesson, we went through several types of function. We found the domain of the respective functions, then also we did some couple of extra work. So we continue in this tutorial by going through the part 2 of functions, and in this part 2, I'll be taking you through exponential functions. We'll do logarithmic functions, so let me list them here. So exponential, you do logarithmic function, then you also do trigonometric function, then you also have the inverse trig. Okay, we have inverse trig, we have what we call hyperbolic function, we also have inverse hyperbolic function, then we have even and odd function. It's very important, even and odd functions. Then we also have periodic function. Periodic function. Then you also go through monotonic functions. Monotonic functions. Then we will do what you call bounded functions. Bounded functions. Then we solve more problems. Okay. So don't be scared. I just listed these types of functions here so that you know what this tutorial entails and you wouldn't leave, suddenly. Okay. So stay glued to your seat and watch this video to the end. Please, if this is the first time you are being on this channel, or if it happens that you are recommended today, do well to subscribe to support the mission, and don't forget to share with people whom you think it's gonna be useful, right? But let's get straight to what we have today. So in our previous lesson, I explained what a function is. That a function is simply um exponential function. A function is simply any piece of instruction, or it's a black box which takes an input, and within the function itself, which is the black box f of x, it gives an output which we are interested in. This function f of x could be anything. Maybe what it does is the input that you give it, it's going to multiply by 2, it's going to divide it by 2. That's the whole idea of function. So anytime you feed it to a respective function, it's going to give you the right output. A function may be single variable or multivariable. I mean, it may take one or more variables. Okay, so if a single variable function is called, that one is what you treat in calculus 1, right? And that's what you're doing. So you do calculus with multiple variables or multivariate calculus. That would be for later parts. So with this, I wouldn't talk much about the basis because we've covered that in our previous lesson. So when you talk about exponential function, it's a type of function. In calculus, you start solving, real calculus questions very soon. But because you don't need to be surprised when you see a function, when they give you a differential and it's a composite, or it's a product of different types of function, you should be able to know. That is why we have taken time to take you through all the different types of functions. So anytime you see a function, you wouldn't be surprised. It wouldn't be something scary, but it will be something relatable. Whenever we take any type of function, what do? We look at what we call the domain of that function, and possibly the range of that function. So these are the two main important factors we look at whenever we are handling any type of function. What will be the domain of this function? Because every function requires an input. But do you think that the function can handle every input? Some function may reject some particular inputs. So the domain is just a set of all possible values that will make our function valid or for it to still act as a function. Range is all the assigned output or the successful output from our function. Then we have the third code domain, which I explained earlier. But code domain is mostly not of any interest because we need a successful output, not a possible output. Right, good. So now let's go straight to what an exponential function. So an exponential function is simply a function f of x given as a to the power x, where a is greater than 0 and a is not equal to 1. So an exponential function is given as any expression which has got a to the power x. So x is a variable, a is a constant, okay? But a is restricted by saying that this a that you know can't be a negative number, okay? Then it should also not be equal to 1. You know that 1 to the power any number is 1. So if I give you 1 to the power x, obviously it's 1. It doesn't make it exponential function, okay? We want to maintain the power there to make it exponential. So exponential function has general notation. I want you to appreciate this as you move. What are some possible exponential functions you may encounter? You can have 2 over 3 to the power x. You can have 2 to the power x. You can have something like 3 to the power negative x. You can have something like square root of 7 to the power x. All these are exponential function. Now, what is the domain of an exponential function? So, you realize that given an expression a to the power x, where a is a positive number, you can confidently say that the domain can be any number actually. Okay. So you realize that the argument, whenever you say argument or the container of a function, it is the part of the function that actually holds the inputs. You realize that the function a to the power x, if I'm to add an input, where does the input go? The input what goes up here, right? So the input up here is of our interest, so that there is no number on earth that when you put it at the input of an exponential function will make it undefined. When you put 0, it becomes 1. When you put infinity, it's infinity. If you put negative infinity, it's 0. So whatever you do, therefore the domain is said to be all real numbers. Take note of that. All real numbers. So the domain of an exponential function is a set of all real numbers. Put it down or R. Then we move to the range. The range. Okay. So what is the range of an exponential function? So the range of an exponential function is going to be what? The range, right? So the range, obviously. So we can say something here. With exponential function, you realize that there is no way we can get negative as an answer. There is no, even if you have 3 to the power negative 2, the answer is 1 over what? 3 squared, which is 1 over 9. Whatever you put it inside the function will give you a positive answer. Therefore, the range will lie between 0, what? Positive infinity. This can also be written as R plus, that is positive real numbers. Okay. So take note this about exponential function. Good. Let's talk about trigonometric function. Sorry, logarithmic function. So logarithmic function. When we talk about logarithmic function, it's any function in the form f of x is given as log the base of a constant a of the function x, where a is greater than 0 and a is not equal to. So this is a general representation for every logarithmic function. So for it to be called a logarithmic function, you simply have to um, have logarithm to the base a of the number x. Look at the condition. You can never have a base which is 1, neither can you have a base which is 0. What are some examples of logarithmic function? So we can have logarithmic function as log to the base 2 out of 3 the number x. You can have something like log 2x is also logarithm. Then you can have this special logarithm log to the base e of a number x, which is called natural log. So if you have not seen this, please, I'm introducing what you call the natural logarithm. Natural logarithm. Take note of that. It's a new thing you might say. Natural logarithm. So when you talk about natural logarithm, it's simply our normal logarithm, but to the base e. So we represent it with a length. So log e x is the same as ln what x. So whenever you see ln x, it means that it's log to the base of e in your calculus course, please. You'll be meeting it all the times, and don't be surprised or don't feel lost when you see that. Let's talk about trigonometric function. So when you talk about trigonometric function, I think this is a little bit familiar, more familiar because it's something you have been seeing, you have been playing around with all this while. Okay, so we call them circular function. Maybe this is your first time of knowing that trig functions are called circular function, like this. Good. So trigonometric functions are also called circular function. With these functions, they are simply cyclic in nature, okay? And they are defined as the functions of angles. So we call trig functions function of angle of a triangle. So functions of angle of a triangle, okay? That is what we call trig function or circular function. Let's analyze some domains and some ranges here. If I have a function fx, I can write the domain here and I write the range here of interest. Let's take a function sin x. Sin x is one of the trig functions, and you know sin x can take any value, whether positive, negative, or even 0. Okay, so the domain is a set of all raw numbers. The range of sin x, or the successful output of sin x, always lie in the range from -1 to 1. Please have this in mind, that the sin x can give out the maximum number to be 1 and the minimum number to be -1, and it's true at all times. A function like cos x, similar to sin x, also has got its domain to be R. Then aside that, it also has a range from -1 to 1 inclusive. Okay, then we also have tan x. Tan x is a little bit different in that if you punch tan x on your calculator, tan 90, okay, that is tan pi on 2, you realize that that gives an undefined. So tan is actually approaching infinity at the angle of 90. Therefore, the domain tries to exclude 90 and its multiples from it. So look at something, it becomes r minus, we have dot 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 because it can be very multiple on the left side, negative 3 pi on 2, comma, negative pi on 2, comma, pi on 2, comma, 3 pi on 2, dot like this. This is the domain of a tan function. We can summarize this nicely in that the domain of a tan, which we can say that d tan is equal to the domain of sec is the same. Okay, so take note of that. The domain of a tangent function, okay, is the same as the domain of a secant or sec 1 over cos. It's very important for you to have that in mind. So once you have this, then we can summarize this simply by saying that the domain is r minus the expression. We have pi on 2 plus k pi, where k is a member of integers. So we are trying to say that when you take 90 plus k pi means that number of what? Revolutions, but tan has a complete revolution around pi. Okay, so the number of pi's you move around is still the same 90. You are just trying to move, I mean, a lot of revolutions. Okay, it's very important for you to take notes. What's the range of tan? The output of tan. Please, tan can produce any output, can even give infinity. So tan is a set of all real numbers for its range. Okay, it's also important. Similarly, the domain of cot 1 over sine is the same as the domain of cosec. Sorry, cot is 1 over tan rather. Then it is the same as the domain of cosec. Okay, and that is also equal to r minus the expression. We have k pi. That's all. Where k is a member of C. So these are some basic stuff for you to put it in your mind as you do calculus, because you will need them alongside when you are doing trig identities, differentials of trig, applications and all that. You've got to know this. So what you're doing is just a build up. Okay. Okay. So we move to inverse trig function. Inverse trig function. Inverse trigonometric function. When you talk about inverse trig function, it may be quite unfamiliar. Okay. So as we have sine, we have cos, we have tan, we have cosec. So let me write them here. Sine, we have cos, we have tan, we have cosec. So that one you say cosec, right? We have cot. We also have the inverse of these functions. Inverse means that I'm going to have sine inverse, I'll have cos inverse, I'll have tan inverse, I'll have cosec inverse, I'll have cot inverse. This has a special name called arc sine, arc cos, arc tan. This also is arc cosec. This is arc cotangent or arc cot. So when you see arc sine in calculus, you are trying to say sine inverse. So therefore, you can say that sine inverse of x is equal to y. So a function y is equal to sine inverse of x. We can translate this and say that your x is equal to sine y. And this is what we mostly use in computation. You appreciate this more when you start solving a lot of differentials using or involving inverse trig. Okay, these identities are so important, which you can't do away with. That's why I've taken time to take you through all the different types of and expose you to the technicalities. So the arctan, arc cosec, arc sine, these are what we call inverse. trig functions. Okay, we wouldn't talk so much here. Let's move straight to what we call hyperbolic function. Hyperbolic function. That's hyperbole, right? So hyperbolic function. So for hyperbolic functions, we are definitely looking at a special types of function. Okay, typically we use sine hash. I don't know if you've seen this on a calculator and you didn't know what it's used for. See sine hash of x. We have something we call cos, right? This is sine and this is cos. So this are something we have tan, right? Tan h of x. So this hyperbolic function has got something to do with complex numbers. Sine x is e to the power x plus e to the power negative x over 2. Sorry, minus. So this is e to the power x minus e to the power negative x over 2. This is e to the power x plus e to the power negative x. Then tan h is obviously going to be what? Sine h x over what? Cos h. So when you divide these two, what are you getting? The 2 and the 2 will cancel out. Then you end up getting e to the power x minus e to the power negative by e to the power x plus e to this gives h. These have got some beautiful applications in geometry which you wouldn't appreciate now as we move forward. And obviously, these hyperbolic functions have got inverses as well. So you can equally have what you call sine h inverse of x. We have cos h inverse of x. And we have tan h inverse of well. So these stuffs should be something you should know. Now let's talk about something important. We call them even and odd functions. When you talk about an even function and when you talk about an odd function, what do we mean? What are you trying to say? What are you talking about actually? Even function and odd function. So when we talk about an even function is an even. I mean, you know what even is, right? So here we clearly define even function and odd function by using the functional notation. So let's first deal with even function before we talk about odd function, okay? So dealing with even function alone. So now, as part of calculus, you may get questions like identify if the following functions are even, odd, or neither. A function may be even, may be odd, or may neither be even nor odd. So it's not like it's only half half. You can if you're not even, that doesn't mean you are odd. You can also neither be even nor odd. Okay. So generally a function is said to be an even function if a function of negative of x is equal to the function of x. That even if you change your input to negative, your function still doesn't it's not affected. That's what we call an even function. So it's symmetrical about the y-axis. You get to know that. So a function is an even function when f of x is equal to f of negative x. That means that no matter the sign of the input comes out as what? Positive. Examples. You have f of x is equal to x squared. Is this an even function? You should be able to test. Whenever they give you any strange function, no matter how complicated that function may be. If you want to test whether the function is an even function or an odd function, simply put f of negative x into that function. That is all. So here to test, you are going to have f of negative x to be equal to open bracket negative x all squared, and this is equal to x squared. Since x squared is equal to x squared, we say that indeed the function is an even function. A function like g of x is equal to negative x to the power 4 plus 2x squared minus 1. How do you know this is an even function? Simply, you found your g of negative x, and that would be negative of the expression negative x to the power 4 plus 2 multiplying negative x all squared minus 1. This gives negative, you know this will be positive, right? X to the power 4 plus 2. This will also be positive, x squared minus 1. And this is the same as what we have here. Therefore, our function is even. Let's see another beautiful even function. A function saying f of x is equal to x sine x. So here, let me clearly say that wherever you see sine, sine is an odd function. Wherever you see sine, anywhere you see sine, is simply an odd function, okay? Whilst you have cos to the odds, an even function. So sine is odd, cos is even. That does not mean that the problem I'm giving to you is going to be even what do you say, odd. You have to test. Sine alone is odd, but that doesn't mean that an expression where sine is inside makes it entirely odd. No. What do we do? Just test. So f of negative x will be equal to negative x multiplying sine of the expression negative x, like this. You have negative x outside, multiplying sine of negative x is negative sine x, okay? Therefore, this gives us negative times negative is what, positive, so we get x sine x back again. Therefore, x sine x is an even function, clearly explained. Let's move to an odd function. When you talk about odd functions, so we have odd functions. This is very similar to the even function with slight difference. So we say that f of negative x is equal to negative f of x. This is what we call an odd function. So here, if you put a negative input, you end up getting negative of your function. Okay, that's a typical odd function. So therefore, if I give you f of x is equal to x squared, right? This will give us testing f of negative x. Oh, sorry, f of x equals x. Even that's too basic for me to use as an example. Let's use a different example here. So giving f of x is equal to negative x cubed plus 2x. How do we test that this is an odd function? Simply, you take f of negative x, and that will give us what? Negative of the expression negative x cubed plus 2 multiplying negative what? X, right? This gives negative. Remember, negative x cubed will give us negative x cubed. So negative x cubed plus this will give us negative 2x. At this point, since you have negative here, you factorize that negative out and you get negative x cubed plus 2x, like this. Therefore, you can clearly see that we started with negative x cubed plus 2x, which is inside here, and we are getting negative of that whole expression. Therefore, our function is odd function. If you do an odd function computation and you are not able to factorize negative 1 out, please, your function is not an odd function. You should be able to take the negative outside. Please take notes. You should be able to take this negative outside. It's very, very important. Okay. So let's give some inferences here before we proceed nicely. Which says that graph of an even function is symmetrical or symmetric about the y-axis. Then a graph of an odd function is symmetrical about the origin. Good. So take these two things to carry on. Now let's move to the next type of function called periodic function, which some of you may not be familiar with. So periodic function, periodic. When you talk about periodic function, period, you are dealing with what? A particular time, or these are functions that are sensitive to time, okay, or period. A periodic function is generally say a function x plus t giving us a function of x. If I have a function within the argument, if I'm able to add a particular constant called t to my input and still get a function back, it means this function is periodic. That is, it repeats itself after some particular time t, where we call that t period of that function. As simple as that. The goal here is that I should be able to give you a periodic function, then you tell me the period of that function. That is the question that you'll be asked here. So I'll give you a nice periodic function. I'll ask you that, hey, tell me the period of this particular function. You should be able to do that. So generally, there are some common periods which you should take note of. When I give you sign of the expression x plus 2k pi, okay, the 2k is standing in for every rotation, okay, every possible rotation about the plane, okay. So let's say that I have sign of the expression x plus 2 pi. Therefore, this should give us sine x. When you rotate sine x around 360, you should get sine x back again, okay. It's very, very important. So therefore, if you are getting sine x back again, then we say that our period is equal to what? 2 pi. Similarly, cos of x plus 2 pi is equal to cos x. Period is equal to what? 2 pi. Then you also have tan of the expression x plus pi. Please take note. Tan repeats itself after 80 degrees revolution, not 360. 80 degrees, 180 degrees, sorry, 180 degrees, not 360. Please take note. So the period for any default tan function is what? Pi. Now, let's solve some problems here. Beautiful problems. Should have this in mind. These are some nice formulas you should have in mind all the time. That the period of any cosine or sine function is given as 2 pi is equal to 2 pi over b, where b is absolute, okay? Then the period of any tan function is given as pi over the absolute of b. You see the difference? Let's solve problems so that you understand. So the b is coming from the expression, if I give you y is equal to sine bx, okay, or y is equal to cos bx, or y is equal to what? Tan bx. So once I give you this expression and I'm saying that the period of this expression is what? 2 pi over the absolute of b, which is the coefficient of what? Of x. So let's solve some problems here. Okay, so I have examples here. It says that y is equal to sine of the expression 3x. Okay, what is the period of this function? The period is simply going to give us 2 pi over what? Absolute of what? 3. And that is what? 2 over 3 pi. And this is the period of the function. I'll give you y is equal to cosine of the expression x over 2. What is the period of this function? To find the period of this function is simply equal to 2 pi over what? Absolute of what? 1 out of 2. And this is going to give us 4 pi. Let's solve the last one. Y is equal to tan 2x. You can use your eyes to tell me the answer. So y is equal to tan 2x. Are going to have pi over what? Absolute of what? 2. Is that not it? The answer is pi. As simple as that. So this is all about periodic function and how to find period of a periodic function. Let's go to monotonic function. Monotonic function, that will be the okay, last but one type of function in calculus which you're going to go through. Now monotonic function is a beautiful type of function and a little bit advanced, not advanced per se. So just monotonic functions. So monotonic functions here is simply saying that x1 is less than x2. Given that x1 is less than x2 over a particular range, or I can assume, let's say, a set of row numbers. So assuming x1 and x2 are members of the row numbers and x1 is less than x2, okay, a function is said to be increasing over its domain. Increasing. So an increasing function is such that f of x1 is less than what? F of x2. If I put x1 in a function and I put x2 in a function and the f1 is giving me a smaller number than the f2, it means my function is increasing over my domain. We have a second type called a decreasing function. So this function keep on decreasing as you progress or as you increase your input. So for this type of function, my f of x1 is going to be greater than what? My f of what? X2, given the initial condition that x1 is less than what? X2. Take note of that. Typical example is e to the power x and e to the power negative x. As I increase the value of x here, what do you see? The function keeps on increasing to infinity. As I increase the function here, it decreases to 0. So these are the increasing and the decreasing types of functions. Now, let's solve some beautiful problems here. The first problem says that show that the function f of x is equal to square root of x minus 2 is increasing function of the domain. Show that the function f of x is equal to square root of x minus 2 is increasing function of the domain. Increasing function of the domain. So to have this solved, the question is simple. You have been given a function f of x which is equal to square root of x minus 2. And they've asked us that we should show that this function is increasing over a domain. The domain is given us, sorry, I didn't write the domain. 2 comma positive infinity. Okay, 2 comma positive infinity. So we have to show that indeed this function is what? Increasing over a domain. How do we do this problem? To do this problem, you say that for an assumed two values x1 and x2 which are member of what? The domain of f. That x1 is less than x2. What do? We will genuinely know that x1 and x2 are members of our domain. Our domain starts from what? 2 and ends as infinity, meaning the smallest number is 2. Therefore, since x1 and x2 are random numbers, I can say that 2 will be less than my x1 and x1 will be less than x2. This is fair point. Once this has been established, our goal is to convert this expression towards our function. How do we modify this interval for it to look like our function? The first thing to do is to do what? Is to subtract 2 from both sides, all sides. Because our function is x minus 2, so we need to subtract 2. So we have 2 minus 2 less than x1 minus 2 less than x2 minus 2. This gives 0 less than x1 minus 2 less than x2 minus 2. The next thing is to take square root. Is that not it? So square root of 0 less than square root of the expression x1 minus 2 less than square root of the expression x2 minus 2. Once you do this, you can clearly see that f of x1 here, if you put x1 in it, f of x1 is given as what? Square root of what? X1 minus 2. F of x2 is given as what? Square root of x2 minus 1 minus 2. Therefore, we can clearly say that 0 less than what? This is what? Our function of what? X1 less than our function of what? X2. And that is all. We have proved it. So meaning that the function of x1 is clearly less than the function of what? X2. And that is what we are talking about. Let's solve another problem. Show that f of x, which is equal to 2x, no, which is equal to 2 minus x all squared plus 1 decreases on negative infinity comma 2 and increase on 2 comma positive infinity, where the domain of f is equal to all real numbers. Show that the function 2 minus x all squared plus 1 decreases on this interval. And for the sake of this tutorial, I'm going to do the decrease part, and I'll ask you, since we did the increase first one, I will can do that on your own for you to get some nice work and understand the concept. Okay, our function f of x equal to 2x, oh, why do I keep on minus x all squared plus 1, and this function here decreases on the interval negative right? Then this is what you're going to solve. So what do we do? What do we do? As usual, you select any random two members of the interval, say x1 and x2, which are members of our all the domain is given as what? Negative infinity. Therefore, you say that our x1 is what? Going to be what? Less than x2, because I mean we are going to do the decrease. So look at something. X1 is smaller than x2, right? X2 is smaller than the biggest number, which is, since you are doing decrease, you interchange. How do we interchange? You are simply going to multiply through by what? Negative. But the reason why you are multiplying through negative is that you want to make this whole function be like what you have here. And the function is minus x. So first it's okay, negative x1 greater than negative x greater than what? Negative. The next thing is our function is having plus 2. Add plus 2. You have 2 minus x1 greater than 2 greater than 2 minus. This goes on plus 2 minus x1 is greater than 2 greater than 0. Now what is 2 minus x1? Function, oh sorry, we are not done. The function is not done. Remember there is plus 1. Even squared, we are not done. So you first square it. So 2 minus x1 all squared greater than 2 minus x all squared greater than 0 squared. This will give us, then we add 1 to it. We have 2 minus 1 all squared plus 1 greater than 2 all squared, right? Plus 1 greater than 0. The answer is simple. 2 minus x1 This is the same as the x1, meaning that indeed our function for the first is second. That is all about monotonic function. I will treat you to solve more problems for you to understand. Let's briefly talk about what we call bounded functions. Bounded functions. So boundary, you know boundary, right? So bounded function is as simple as you know. So bounded functions, boundaries, bounded functions. So when you talk about bounded function, a function is said to be we have bounded above, then we have bounded below. So a function is said to be bounded above if there is a certain number within the domain, okay? Say u, which is a member of the domain, right? And it may be a member of all real numbers, so that the function of u, right, is always less than or equal to u. You get it? We are saying that, oh, so that a function of x, sorry. We are saying that for a bounded above, there is a certain member of the domain, so that the function of x is always less than or equal to this number. So it means that it's bounded above, meaning your set of outputs can never be greater than that. It's the upper bound or upper boundary. The same thing for this, a function set that L, which is a member of all real numbers, so that your function of x is always less than what? This. We call it bounded lower or lower boundary. Okay, that is the idea of upper bound. Okay, if I give you f of x is equal to x squared plus 1 within the interval 0 less than equal to x less than equal to 1, right? I can genuinely say that 2 is an upper boundary of this function. Okay, so far as I'm within this interval from 0 to 1, the highest I can get is 1. When I put 1, I get 2. So 2 is an upper bound. The lowest I can get will be what? So this one is for upper boundary. So let's just look at that. So given a function f of x is equal to x minus 1. Lower boundaries, mostly we look at functions that are decreasing over an interval which is from 0 to 1. The lower boundary can be perfectly negative 1. You get that right? Powerful. Then the final thing and the function that I would like us to talk about is what we call the maxima and minima. So when you talk about the maxima and the minima, we are simply talking about this type of function. So I believe that in SHS, let me draw a proper one. So you have something like this, something like this, something like this. In high school, you learned about calculating the maximum value. You have what you call the global maxima, and you have the local. So local and global minima or maxima. This is just a reflection on those stuff. So that the lowest point here is the global, then the lower point here is local, the lower point here is local, right? Then this one is a local maxima. Local maxima, you can have a global maxima here. So these stuffs are not so difficult, and I believe that just have a refreshing mind. Now let me give you some random questions of that. Now, so random questions. First question, you have find the period of the function f of x equal to cosine of the negative 2x plus pi on 3. Find the period of this function. You are simply going to have, as you know, pi over what? Absolute. What's that? Our b is absolute, so pi over what? Absolute. The answer is what? Pi Simple as that. Determine determine whether even or odd or neither for this function which is given as e to the power x squared plus natural log of the expression absolute of x plus 1. Is this function odd or neither? You can see something here that when I put in the value for x, right, you should do the so mostly for even odd, you do for even first. So f of negative x. If you won't say even, well, anytime they give you this problem, just put f of negative. The outcome will tell whether it's even. What do you get? E to the power negative x all squared plus natural log absolute of what? Negative x plus 1. This end up giving us e to the power x squared back. Plane of this is still what? X plus. Therefore, this function is a perfect. So I think we'll end here. I'll see you in the next session talking about limits and continuity. You solve more problems on that. Then we move to differentials. Then the journey begins. These ones are all just opening your eyes. Thank you for being with us in this session. Please do well to subscribe and don't forget to share to friends too.